A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
So, Herman, I was looking at our API billing for the last month, and something really struck me as odd. We ran two nearly identical prompts through two different frontier models, GPT-4o and Claude 3.5 Sonnet. The semantic intent was the same, the word count was identical, and yet the token counts and the final costs were noticeably different. It is like there is this invisible wall between what we type and what the model actually perceives.
Herman Poppleberry here, and you have hit on one of the most fundamental, yet often overlooked, parts of the modern artificial intelligence stack. That invisible wall you are talking about is tokenization. It is not just a simple step of turning words into numbers. It is the model's entire perception of reality. If the model cannot tokenize it efficiently, it basically does not see it clearly. Our housemate Daniel actually sent us a prompt this morning asking about this. He wants to know why different models use these disparate tokenization calculations, and whether this whole process is a hard-coded architectural constraint or just a modular choice made during pre-processing.
That is a great question from Daniel, because it gets to the heart of how these machines actually process human language. We talk about large language models as if they understand English or Hebrew or Spanish directly, but they do not. They are essentially massive math engines that operate on vectors. So, today we are going to deconstruct the tokenization tax. We are going to look at why your prompt might cost more in one model than another, even if the text is the same. We are going to dive into the engineering trade-offs that lead to these discrepancies, and why, in 2026, we are still fighting with subword units.
And we should probably start with the basics for a second, just to set the stage. Tokenization is the bridge. It is the process of breaking down a string of text into smaller units called tokens. These can be whole words, but more often they are sub-word units. Think of the word high performance. A tokenizer might break that into high, a dash, and performance. Or it might break it into even smaller chunks depending on its vocabulary. The model does not see the letters. It sees a sequence of integers.
Right, and the key thing to understand is that the model does not see the letters H, I, G, H. It sees a specific index number associated with the token high. So the first big divide we need to talk about is the algorithm used to create these tokens. Most people have heard of byte pair encoding, or BPE, which is what OpenAI uses. But then you have things like the unigram language model used in Google's sentence piece. Herman, why does the choice between BPE and unigram even matter for the final output?
It matters because of how they build their vocabulary. Byte pair encoding is a bottom-up approach. It starts with individual characters and then iteratively merges the most frequently occurring pairs of tokens into a new single token. It is very deterministic. If you see the letters T and H together a billion times, they eventually become a single token. Unigram, on the other hand, starts with a massive vocabulary and iteratively removes tokens that increase the overall likelihood of the training data the least. It is a probabilistic approach. BPE is great because it ensures that any string can be tokenized, even if it is just a sequence of individual bytes. Unigram is often seen as more flexible for morphologically rich languages because it treats tokenization as a statistical optimization problem rather than just a frequency count.
So, it is essentially a compression problem. But here is the catch. If you have a larger vocabulary, you can represent more complex ideas with fewer tokens. That sounds like a win, right? You save money on the API and you fit more into the context window. But I imagine there is a trade-off on the model side. You cannot just have a vocabulary of a billion tokens.
There is a massive trade-off. This is where we get into the vocabulary size debate. Most modern large language models, or LLMs, use a vocabulary size somewhere between 32,000 and 128,000 tokens. If you go with a huge vocabulary, say 256,000 tokens, your embedding matrix becomes enormous. Remember, every single token in that vocabulary needs its own vector representation in the model's memory. If you have a model with a hidden dimension of 4096 and you double your vocabulary size from 100,000 to 200,000, you are adding hundreds of millions of extra parameters just for the embedding layer.
That is memory that could have been used for deeper layers or more attention heads. It is a balancing act between the efficiency of the input and the memory overhead of the model itself. If you are running on an H100 or a B200 cluster, every gigabyte of VRAM counts. If your embedding matrix is taking up 5 gigabytes just to store the dictionary, that is 5 gigabytes you cannot use for the actual reasoning layers. This is why researchers spend so much time optimizing the tokenizer before they even turn on the big GPU clusters. They are setting the foundation for how the model will perceive every single piece of information for its entire lifecycle.
And that brings us to the February 26 update to the tick token library. OpenAI actually pushed some optimizations for multilingual character sets recently. They are trying to find that sweet spot where they can represent non-Latin scripts more efficiently without ballooning the model size. Because if you look at low resource languages, like Swahili or Khmer, the tokenization tax is real. In some older models, a single sentence in Khmer could take 10 times as many tokens as the English translation. This is not just a cost issue, it is a performance issue.
I remember we touched on that in episode 666 when we talked about the tokenization tax as a hidden language barrier. It is almost like a digital divide. If a model is trained primarily on English data, its tokenizer is going to be incredibly efficient at English. It will have single tokens for common English words. But for a language it is not seen as much. It has to fall back to character level or even byte level representations. That makes the sequence length explode. If you are a developer in Nairobi or Phnom Penh, you are literally paying more for the same intelligence because the model's eyes are not calibrated for your script.
And sequence length is the killer because of the attention mechanism. As we have discussed before, the computational complexity of standard self-attention is quadratic relative to the sequence length. If your tokenizer is inefficient and turns a 100-word paragraph into 500 tokens instead of 150, you are not just paying more in dollars, you are hitting the quadratic wall much faster. The model has to work significantly harder to maintain coherence over that longer sequence. It has to store more in the KV cache, which slows down inference and limits how many users you can serve simultaneously.
So, to Daniel's point about whether this is intrinsic or modular, if I have a pre-trained model like Llama 3, can I just swap out the tokenizer for a more efficient one? Or is the model's understanding of language permanently baked into the specific tokens it was trained on?
That is the million-dollar question. Technically, the tokenizer is a pre-processing step. You could take the same text and run it through a different tokenizer. But the model's weights, the actual neurons if you will, are mapped to specific token IDs. If token number 5042 meant apple during training, and you swap the tokenizer so that 5042 now means orange, the model is going to be completely incoherent. So, while the algorithm for tokenization is modular, the specific vocabulary and the mapping are absolutely intrinsic to the trained model weights. You cannot just swap it after the fact. You are married to your tokenizer from the moment you start pre-training.
That explains why we see such a focus on efficiency versus generalization. I have noticed that some models, like the early Llama versions, used a relatively small vocabulary of around 32,000 tokens. Herman, why would they do that when they could have gone bigger?
It is about robustness. A smaller vocabulary forces the model to learn the building blocks of language rather than just memorizing whole words. It is the difference between learning how to spell using phonics versus just memorizing the shape of every word in the dictionary. The phonics approach is more robust when you encounter a new word or a typo. If the model sees a word it does not know, but it is made of familiar subword units, it can still infer the meaning. If you have a massive vocabulary that includes every possible variation of a word, the model might struggle if it sees a version it has not encountered before.
That is a compelling, counterintuitive point. So, a highly optimized tokenizer that compresses English perfectly might actually be more fragile when it encounters noisy data, like a chat transcript with lots of slang and misspellings. Whereas a dumber tokenizer that breaks things into smaller pieces might actually help the model generalize better, because it is seeing the atoms of the language more clearly.
Precisely. And we see this in the performance drop-off when you use a tokenizer that was not designed for the task at hand. Think about code. If you use a standard natural language tokenizer on Python code, it is going to be a disaster. It might treat every single space or indentation as a separate token, or it might struggle with specific syntax like brackets and underscores. This is why models like StarCoder or even the later versions of GPT use specialized tokenizers that are optimized to handle the repetitive and structured nature of programming languages. They might have specific tokens for 4 spaces, or if name equals main, to keep the sequence length manageable.
It makes me think about the second-order effects on things like retrieval augmented generation, or RAG. We talk about RAG all the time as the solution to model hallucinations, but there is a tokenization trap there too. If your embedding model, which is used to find the relevant documents, uses a different tokenizer than your LLM, which is used to generate the answer, you can get these weird semantic mismatches.
Oh, that is a deep cut, Corn. You are talking about the mismatched tokenizer problem. If the embedding model sees the word transformer as a single token, but the LLM sees it as trans and former, the mathematical representation in vector space might be slightly shifted. It is like trying to translate a book from French to English using a dictionary that was written for a different dialect. You get the general idea, but you lose the nuance. In high-stakes applications like medical or legal RAG, that nuance is everything.
It really highlights that tokenization is not just compression. It is a lossy mapping. We think we are just shrinking the text, but we are actually defining the semantic boundaries. If the tokenizer decides that two concepts belong in the same token, the model will have a much harder time distinguishing between them later on. It is like trying to paint a masterpiece, but you only have 5 colors. You can mix them, but the fundamental granularity is limited by your palette.
And this is why there is a whole movement toward token-free models. Have you looked into things like CANINE or ByT5? These are models that operate directly on bytes or characters. They completely bypass the tokenization step. The idea is that if you remove the tokenizer, you remove the bias, the language barriers, and the vocabulary constraints. You are feeding the model the raw data, the actual bytes that make up the text.
I have seen those, but they have not really taken over the world yet. Why is that? If tokenization is such a headache, why are we all just using byte-level models?
It goes back to that quadratic complexity we mentioned earlier. If you operate at the byte level, your sequence length becomes massive. A single word that might be 1 token in GPT-4o could be 10 or 15 bytes. Now multiply that by a whole prompt. You are looking at sequences that are 10 times longer, which means the computational cost for the attention mechanism goes up by a factor of 100. We just do not have the compute to make byte-level models as efficient as token-based models yet. We are essentially using tokenization as a form of pre-attention compression to keep the math manageable for our current hardware.
So, for now, tokenization is the necessary evil that allows us to have these massive context windows. It is the compromise we make to keep the math manageable. But it does mean that as developers and users, we have to be smarter about how we interact with these models. We cannot just assume that a word is a word. We have to think about the tokenization tax every time we hit the enter key.
Right. And that brings us to the practical side of this. If you are building an application, you should be auditing your prompts for token efficiency. There are these great tokenizer visualizers out there. OpenAI has one for TikToken, and there are others for the Llama and Claude models. You can actually paste your prompt in and see exactly how the model is chopping it up. Sometimes, just changing a single word or a piece of punctuation can save you 20% on your token count. For example, some tokenizers treat a space followed by a word differently than just the word itself.
That is a great tip. I've actually noticed that using specific delimiters can make a difference too. If you use something like triple backticks or specific XML style tags, most modern tokenizers are trained to see those as single tokens or very clean breaks. If you use weird custom symbols, you might find the tokenizer struggling and creating a bunch of fragmented tokens that drive up your cost. It is about working with the grain of the tokenizer rather than against it.
And it is not just about cost, it is about performance. If the tokenizer fragments a key piece of information, like a technical term or a person's name, the model has to work harder to reassemble that meaning in its hidden layers. If you can keep your key terms as single tokens, the model's performance generally improves. It is about making the input as clean as possible for the model's internal representation. Think of it like feeding a machine. If you give it pre-cut pieces that fit perfectly into its gears, it runs smoothly.
You know, it is funny we are talking about this as a modular choice, but in a way, it is almost like a biological constraint for the AI. Just like humans have a limited range of frequencies we can hear, or a specific spectrum of light we can see, the tokenizer defines the sensory input range for the LLM. If it is not in the vocabulary, or if it is represented poorly, the model is essentially deaf or blind to that nuance. We discussed the hidden layers of prompts in episode 65, and this is really the very first layer.
That is a perfect analogy, and it explains why different companies are so protective of their tokenizers. It is a piece of intellectual property that defines the efficiency of their entire ecosystem. When we discussed securing model weights in episode 671, we did not spend much time on the tokenizer, but it is a critical part of the stack. If someone steals your model weights but does not have your exact tokenizer, the weights are basically useless. They are a map without a legend.
So, looking ahead, do you think we are going to see a shift toward more specialized tokenizers? Or are we moving toward a universal standard? It seems like every new model release comes with its own custom version of BPE, or sentence piece.
I think we are seeing a move toward larger, more inclusive vocabularies, like the 128,000 token limit we are seeing in the latest frontier models. The goal is to make the tokenizer as invisible as possible across as many languages and domains as possible. But I also think we will see specialized models for things like medicine, law, or chemistry that use very specific tokenizers. If you are a medical AI, you want words like deoxyribonucleic acid to be a single token, not a fragmented mess of 10 different subwords. It saves context space and improves the model's ability to reason about complex molecules.
It makes total sense. If you are working in a specialized domain, you need a specialized set of eyes. It is about efficiency and precision. But for the general purpose models most of us use every day, we are stuck with these general purpose tokenizers that are biased toward common English usage. This is why staying updated on library changes is so important. Like that February update I mentioned. It was a subtle change, but for developers working in multilingual contexts, it was a huge deal. It changed the cost structure and the performance profile of the model overnight.
It really goes back to what we talk about on this show all the time. The stack is deeper than you think. When you type a prompt, you are not just sending text to a brain. You are sending it through a complex pipeline of preprocessing, embedding, and then finally the transformer layers. Tokenization is the first gatekeeper in that process, and it is a gatekeeper that we can actually influence. By understanding how BPE works, by being aware of the vocabulary size of the model we are using, and by testing our prompts in tokenizer visualizers, we can be much more effective users of this technology.
I like that. It is about taking control of the interaction. Instead of just shouting into the void and hoping the model understands, we are learning the language that the model actually speaks. And that language is tokens. It is a mathematical language. And once you start seeing the world in tokens, you realize why the models make the mistakes they do, why they struggle with certain rhymes, or why they get confused by certain wordplay.
For sure. We actually did a whole episode on that, episode 699, about whether AI can get a joke. A lot of that comes down to the tokenizer. If the joke relies on the way a word is spelled, or the way it sounds, and the tokenizer obliterates that information, the model is just guessing based on semantic context. It does not have the raw data it needs to actually get the joke. It is the same reason why models used to struggle with simple tasks like counting the letters in a word. If the word strawberry is just 2 tokens, straw and berry, the model does not actually see the individual letters unless it has been specifically trained to reconstruct them.
That was a huge moment for a lot of people when they realized that. It felt like a magic trick being revealed. You realize the model is not actually reading the letters, it is just processing these numerical blocks. It makes the whole thing feel much more like the sophisticated math it actually is, rather than some kind of mystical intelligence. And that is where the real power is. Once you strip away the mysticism and look at the engineering, you can start to solve real problems. You can build better RAG systems, you can lower your inference costs, and you can create more reliable AI applications.
It all starts with the humble token. So, to wrap up the first part of our deep dive here, we have established that tokenization is this critical bridge between human language and vector space. It is a choice made during the training phase that becomes an intrinsic part of the model's architecture. Different models make different trade-offs between vocabulary size, memory overhead, and computational efficiency. And while we might eventually move to byte-level, token-free models, for the foreseeable future, we are living in a token-based world.
And that world is governed by the tokenization tax. Whether you are paying for it in dollars or in context window space, you are paying it. The goal is to be an informed taxpayer. All right, let's shift gears a bit and talk about some of the more practical implications for developers. If I'm building a chain of models, say I'm using a small model for classification and a large model for generation, how worried should I be about tokenizer compatibility?
You should be very worried, Korn. This is one of the most common points of failure in complex AI workflows. If you are passing data between models that use different tokenizers, you are essentially playing a game of telephone. Every time you re-tokenize the text, you risk losing a little bit of the original meaning or introducing subtle artifacts. For example, if Model A uses a tokenizer that strips trailing spaces and Model B expects them for its formatting, your output is going to be a mess.
So, the best practice would be to try and stay within the same family of models whenever possible, or at least use models that share a similar tokenizer foundation.
If you are using the OpenAI ecosystem, try to stick with models that use the same version of TikToken. If you are in the open source world, look for models that were trained on the same base tokenizer, like the Llama 3 tokenizer, which has become a bit of a standard for other fine-tuned models. It just simplifies everything. Your character counts match up, your token limits are consistent, and you don't have to worry about those weird semantic shifts we talked about.
And it is also about predictability. If you know exactly how your text is going to be tokenized, you can build much more robust prompts. You can use specific formatting that you know the model will handle well. Herman, what about the cost of inference? We mentioned this briefly, but it is worth going deeper. When you are running a high-volume application, a 10% difference in token efficiency can mean thousands of dollars a month.
It really does. This is why companies like Anthropic and OpenAI are constantly iterating on their tokenizers. They want to make their models cheaper to run without sacrificing performance. It is a competitive advantage. If your model can process the same amount of information in 20% fewer tokens, you can either lower your prices or increase your profit margins. It is a race to the bottom in terms of cost, but a race to the top in terms of efficiency.
It really changes the way I think about model selection. It is not just about the benchmarks or the parameter count. It is about the entire input-output pipeline. The tokenizer is the first and last thing the data touches. It is the bread in the sandwich, corn. Without it, the whole thing just falls apart.
I am going to be thinking about that analogy every time I see a token count now. So, what is the takeaway for our listeners? What should they actually do with this information?
First, if you are a developer, audit your prompts. Use those visualizers we mentioned. See where your tokens are going. You might be surprised to find that a certain way you are formatting your data is incredibly inefficient. Second, be mindful of the tokenization tax when working with non-English languages. Don't just assume the costs will be the same. Check the token-to-word ratio for your specific language.
And third, stay updated on these library changes. Things like the TikToken update in February 2026 can have a real impact on your workflows. Don't just set it and forget it. The infrastructure of AI is still evolving rapidly. And finally, don't be afraid to experiment with different tokenization strategies if you are training or fine-tuning your own models. The choices you make there will define the performance of your model for its entire existence. It is worth the extra time to get it right.
That is a great list. It is about being proactive and informed. We aren't just passive users of these models, we are partners in the process. And the more we understand the underlying mechanisms, the better partners we can be. It has been a fun one to dive into. Tokenization might seem like a dry topic on the surface, but once you get into the weeds, it is actually one of the most fascinating parts of the whole field. It is where human language meets machine logic.
It really is. And I want to thank Daniel for sending in that prompt. It was a great excuse to go deep on something that affects all of us, even if we don't always realize it. If you are listening and you have a weird prompt or a technical question you want us to tackle, we would love to hear from you. You can find a contact form on our website at myweirdprompts.com.
Yeah, and we are also on Spotify, so you can subscribe there to make sure you never miss an episode. We have a huge archive of over 1,000 episodes, so if you enjoyed this one, there is plenty more to explore. Check out episode 635 for more on the hidden layers of every AI prompt. It pairs really well with what we talked about today. And hey, if you've been enjoying the show, a quick review on your podcast app really helps us out. It helps other curious people find us and join the conversation.
It genuinely makes a difference. We appreciate all of you who have been with us for the long haul. I was thinking about your bread and the sandwich analogy, corn. If the tokenizer is the bread, what does that make the model weights? The meat?
I would say the model weights are the secret sauce, Herman. That is where all the flavor and complexity comes from. The tokenizer just holds it all together and makes it easy to consume.
I like that. But then what is the prompt? The lettuce?
The prompt is the customer's order. It is what tells the kitchen exactly what kind of sandwich to make. And if you don't speak the same language as the chef, you might end up with something you didn't expect, especially if the chef only speaks tokens.
You have to order in tokens if you want the perfect sandwich. Before we go, I actually had one more thought about the byte level models. If we do eventually get the compute to make them efficient, do you think we will look back on tokenization as this weird primitive era of AI? Like how we look back on dial-up internet?
I think that is exactly how we will see it. We will tell our grandkids about the days when we had to break words into little pieces just so the computer could understand them. And they will look at us like we are crazy. They will be living in a world of continuous fluid information processing where the idea of a token is completely obsolete.
It is a wild thought. The transition from discrete tokens to continuous byte streams. It is almost like moving from film to digital video. You lose the frames and just get the flow.
We're in the frame-by-frame era of AI right now, but the future is definitely fluid. I, for one, am excited to see it. But for now, I guess I will keep an eye on my tick token counts.
Smart move. Every token counts. Corn.
Every single one. One last thing, Herman. Did you see that paper about the new hierarchical tokenizers? The ones that try to combine the best of both worlds?
I did. The ones that use a small base vocabulary but can dynamically create larger tokens on the fly? It is a really clever approach to the vocabulary size problem. It is like having a small set of tools that can be assembled into complex machines whenever you need them.
Precisely. It feels like a very elegant middle ground. It maintains the efficiency of a small vocabulary for the model's memory, while giving the flexibility of a large vocabulary for the input. I wonder if we will see that in the next generation of frontier models.
I wouldn't be surprised. It is all about finding those little efficiencies that add up to massive gains. That is the name of the game in 2026.
It really is. This has been episode 1066 of My Weird Prompts. I am Corn Poppleberry.
And I am Herman Poppleberry. Thanks for listening, and we will catch you in the next one.
See you guys.
Goodbye.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our show.